Hi, so without further mumbling, I will give you the theory, the beautiful theory of Haar measures, and I'll try to give you the overview first, without being very specific, like what's the point? Let's start with a circle. I paint the circle here with radius 1 in R2. So my whole world is just this circle, right? The plane doesn't exist. Is there so that's a set, that's my circle, that's X. Is there a natural, in a way, measure on this set? I guess most people would say yes, that there is a natural measure. What means natural? Somehow it doesn't differ in different directions. So if I have, if I have an opening here of angle theta, and consider so this is like a interval on my circle, what should be the length here? Well, it should just be like if you straighten this out and measure the actual length, that's probably the natural measure. Then you can argue, should we measure in gradients, degrees or radians? That means, is this full length here 360 or 2 pi? Or maybe we should normalize so the full length is 1. This is a detailed question, but anyway, so we have this mapping from the interval from 0 to 2 pi if we use radians, yeah, such that now I have this set here, and this map I call it phi, and then I map this back here, so then I get some interval here, and then you would say that, all right, so here's my I. So mu of I defined by Lebesgue measure phi minus 1 of I. That's probably the natural somehow measure we can think of here on the real line. Why is it natural? Well, another way of thinking about it is if you took several variables too, then you see that this is just the arc length measure we have reinvented here, right? So it's natural in that sense, but we don't want to here stick in the framework of Rn and arcs and surfaces or whatever, because we did that in several variables. Here we want to go into more abstract mathematical spaces, and I'll try to highlight why this is interesting. So if you want to think of this circle here, not as a line with a bit of bending to it, but rather some sort of mathematical object, what is it? Does it have some additional structure without being just looking around? Well, let's, instead of thinking of this as R2, think of it as the complex plane. Yeah, so this is the imaginary axis, and here's the real axis. Then this map here, so here's my theta axis. So the map phi of theta would then be e to the I theta. Yeah? Why did I switch from R2 to complex numbers? Because complex numbers can be multiplied. And if we multiply complex numbers on the circle, we stay on the circle because the radius doesn't change. So this map gives a representation of this set X here. And what do we have? So we take two elements of X, so e to the I theta and e to the I phi in X, and then we can multiply them. And what is that? Well, we get the new number by just adding up the angles, right? So if I remove this interval here, so this guy is theta, and then phi is somewhere nearby it, then this is theta, this is phi, and then theta plus phi becomes, this guy here, maybe. more or less. This angle should be more probably. Okay, so then we see that, well, first of all, we see that this is a group. The mathematical object where you can multiply things and stay within the object is called groups. This is a group with identity, because if you multiply with 1, you don't change. There are groups that doesn't have identity and so on. Yada, yada. This is 9.1 groups, and then you want to put some topology on them and so on. But I don't want to get stuck in the swamp of technicalities. I want to keep the vision straight a bit or up. You know, why are we doing this here? Okay, so this is a group, and the group structure here corresponds to addition here. Yeah. So R with plus, that is a group, but it is an infinite group. Yeah, all right. But then you can do R modulo 2 pi, so identify, you know, 0 and 2 pi and 4 pi and so on are the same kind of number. And then plus, this is also a group. And well, what do we have? Here we have like a natural measure, which is the Lebesgue measure. And why was it natural? Because if I have some set A and I move it some distance t, then the Lebesgue measure didn't change. Same here, if I consider some set here A, and this measure, like if I move it to the right, and I'm going to start here, as long as I come in on the left, which this modular thing will help me to do, the measure of the moved set is the same as the measure before we moved it. So lambda, right, I mean, this set you can identify it easily with just 0, 2 pi open, and then you just, everything that goes out here, you push it in there. And then on this space here, we have lambda. So we get lambda restricted to this, seen as a group. It's also translation invariant. Meaning that lambda of a theta plus some set E is equal to lambda of the set E. Now, right, so anytime you have a group, you can start asking them, is there a set which has this translation invariance? And the answer is, that's what Haar measures is about. The answer is yes. There exists always on any locally compact Hausdorff group, there exists one unique measure up to rescaling, which is translation invariant. So rescaling, I mean, all right, so here we know the Lebesgue measure is unique if we want the unit interval to have length 1. If we wanted to have length 2 or whatever, then we just take this guy and multiply it with 2. So except for such silly differences, this measure is unique. Now, one issue with groups, so plus notation usually indicates that it doesn't matter, it's commutative, right? It doesn't matter. And then if you do E, so theta plus E or E plus theta, that's the same thing. In general groups, this is not the case. So we separate between right Haar measure and left Haar measures. And we usually use multiplication instead of plus, because multiplication is not always commutative. In the end, you just pick a symbol for your mathematical operation, right? But so we usually use this. Here, of course, in this group, it's again commutative, but we will see examples of groups that are not commutative. Anyways, the bottom line here is that there are as long as your group is compact, so the full group has finite measure, the difference between left and right Haar measures disappears. So there's only one Haar measure, and then we can talk about the Haar measure. In infinite groups, so just locally compact groups, there could actually be a difference, and we will look at that later on. But let me try to, instead of getting stuck there, give you something that the book doesn't really give, namely, why are we doing this? And I want to talk about matrix theory. All right. So instead of a circle, I can think of this as the amount of unit vectors in R2. Right? If I am in R3, then still the unit sphere, and identify that with one vector. Once I've chosen him, let's say I want to choose another vector with the requirement that he's orthogonal. So first here, to specify a vector like a point on the planet, you need azimuth, the angle with the North Pole, and then you need another angle to say where you are with respect to the Greenwich meridian or whatever it's called, right? So you need two angles to specify him. Now, once that is done, you have a restriction that you want the second guy to be independent of him. So you just need one more angle to specify him. So this is like if some giant comes and kicks the Earth out of place and we start wobbling in space. You want to describe the Earth's position at a certain point. You need to say, well, where is the North Pole pointing now towards some universal reference systems. And once you have said that, you need to say where is Greenwich pointing with respect to this sort of like the giant's universal framework, whatever. But you need three angles to specify this. Did we now specify exactly how is the Earth pointing? Yes, because if you go west from Greenwich, you will end up in New York, even if the giant kicked it. But you could actually also kind of think that the Earth got flipped back forward, so that if you go west from Greenwich, you end up in Peking. And that's like if you choose the third vector here. Now you want it to be orthogonal to these two. You can either go this direction or that direction. So there's a plus minus one choice here. And if we decide that the first one and the second, that is rules like physics, right? If you just decide how these should be oriented, then that doesn't matter. So this leads to the orthogonal group and the special orthogonal group. The point is that if I have, this is my E1, this is my E2, and this is my E3, whether I've decided which way he's pointing or not, I can now think of this as a new reference word. Yeah, so as long as the Earth goes wobbling through space, we don't really notice it, well, unless we get further away from the sun, maybe it's cold. But point is, for us on the planet, we still just need these three guys, right? So we can organize this in a matrix where we put E1, E2, and E3, and these vectors are orthogonal. So the collection of all such is called the orthogonal group with three variables, and then if you force the third guy to be this guy to be follow some thumb rule, whatever. So if you want the determinant here to be +1, technically, then that's the special orthogonal group. 98% sure. I should check Wikipedia, but I'm afraid Arne is going to comment in a minute. So I just go on talking. Point is that this is also a group. Okay? So now, if I have U in O3 and V in O3, then U times V is a new matrix in O3. How do we see that? Well, we actually don't see it. This is just matrix manipulations. What does it mean to be Okay, so these matrices that look like this are called unitary. So orthogonal group is a bit unfortunate choice of terminology, but okay, you see where it comes from, right? But anyways, so unitary, a way of checking that, and here you need to know some matrix theory, is to check that this is equal to the identity, where here's the adjoint, and that's the same as doing that. If this is the identity, then this is also going to be the identity. So such matrices are called unitary. So in other words, the inverse and the adjoint is the same thing. Now, so if we have this for U and V, then we just need to check this for the multiplication. And then you see the adjoint will flip order here. So you get the V star, U star, U, V star. And this is identity. And then this one hits this guy. So this is identity, right? And the same determinants are multiplicative. So if determinant of U is positive and determinant of V is positive, and multiplication would have a positive or +1 determinant. From here, this rule you figure out that the determinant of a unitary matrix is always either +1 or -1. The unitary group, or the orthogonal group, shows up in all sorts of applications in physics and matrix theory and so on. Random matrix theory, for example. And here, so let me see. So why would we want a measure on this orthogonal group that behaves a bit like this translation invariant? So like a Lebesgue measure for the orthogonal group. So this is certainly like a round object, sort of intuitive. Just think of this, right? It's some sort of round object, but yeah, you know, the first vector you identify it with a sphere, and then the second guy is still has a field, so it's some sort of multi-dimensional round object. It's not really a ball; it's higher dimensional. But thinking of him, there should be some sort of measure on this higher dimensional round thing, which gives the full thing, the whole set, measure 1, and that doesn't see sort of some rotations, yeah? Doesn't see multiplication by a new matrix. And that's what Haar measure does. Yeah, the Haar, what we learn in this chapter is that such a measure exists, and it doesn't matter. I mean, here, this is fascinating. So if I do this, that's usually not the same as this, right? But still, it will turn out that the measure of U times a set E, so now E is a set, U is just a matrix, is the same as the measure of E times U. Now that's a bit unexpected because these are different sets. Some of you close your eyes and think about round balls and higher dimensions, maybe you feel it's natural, but why is this true? We come to that in section 9.3. So this is true whenever the group is compact, otherwise not. So there's something called a modular function, yada. But okay, at this point, I just want to say that the Haar measure on this guy has this property, because this is important. What we will do now is we will multiply both from the left and from the right. So, what is used to describe a huge amount of phenomena in physics and what shows up all the time in mathematics is something called self-adjoint matrices. Let me call them HN. So this is the set of all matrices A. So matrices n times n, complex or real. Let's do them complex. Okay. Such that A is equal to A star. Now, what does this mean? It means, so star means take a transpose and flip, right? So here you have A11, A12, A21, A22, yada. And then, so if this is A, then A star is going to be equal to A11, A22, here A21 bar and here A1, 2 bar. So we realize that we get this relationship that basically here we will have A1, 2 complex conjugate, and on the diagonal, okay, so here we also get the bars. We see that whatever is on the diagonal must be real numbers, and out of the diagonal we allow complex numbers, but with the restriction that this is the complex conjugate of that guy. So now I can identify. So basically, if I want to parameterize this, I want to think of this as some sort of I want to work with this object of all Hermitian matrices. Then there's a natural somehow identification here. So first, I just stash these guys, right? So first I do A11 up to ANN. So these are real numbers. And now I have to fill in these guys, which are n minus 1 times n minus 2 divided by 2 in total amount, but they're complex, so they are real part and another real part. So first comes this guy is Rn. Then I have real part of A12, yada, yada, yada. This will be Rn minus 1, because I have n minus 1 here, and n minus 1. So this is a triangle of base n minus 1 and height n minus 1. And then the total amount of elements there is this. And then we get the imaginary part of the same numbers. Right? So then we have another. So many amount of real numbers. Now, with this, I can create an identification. Well, some sort of map. Here's my ON. No, my HN. And this map, we call it phi. Right? So this is just I mean, we know measure theory on R to the power, high dimensional R. I don't know what, if you sum up here, what number you get, but probably n squared, right? Looks like it. Okay, so this is isometrically isomorphic to Rn squared. But this is a really shitty representation of numbers, of matrices in Hn, because all right. If you are used to working with matrix theory, you never think of Hermitian matrix in terms of just the numbers in the matrix. You think of it in terms of the spectral decomposition, which we learn in linear algebra or functional analysis, maybe. So what's that? It says that if you have a matrix A in Hn, then you can always write it as A times U, and then some diagonal matrix with the eigenvalues on the diagonal, and then U star. Okay, and these are unitary matrices. And here you just have n numbers. You can think of them as the first n here, but they are not the same. So armed with this, we want to be able to, so now we want to work with measures on the space of all possible matrices. If this is probability theory, I want to say, what's the probability of a certain matrix A to pop up in my experiment, whatever. I need a measure now, measure U that lives on Hn and takes values of a positive measure, right? Something like this. If I have a measure like this, it would be many natural measures naturally appearing. They don't see this guy. They don't care about him and him, but it's the same guy, right? They just care about what's on the diagonal, what are your eigenvalues. And to be able to work with this in a good way, you then need, this is where this Haar measure comes in, but unfortunately it's 2 minutes past 3 and Arne is waiting outside. So I'll get back to this topic at the next convenient occasion. All right, so I told them to not erase. You see here, Lord Stowe, that Swedish means don't erase, and of course they erase it anyway. Anyway, let me backtrack a bit, and I'll start by correcting some of the wrong things I said yesterday, and then I'll proceed to say more wrong things today. So that's the plan. Well, anyways, I'm not a group theory guy, so I got these groups a bit mixed up. We have the orthogonal group, n by n matrices. That is, the name orthogonal is correct. It's not the unitary matrices. This, so the difference is that these are real valued. So columns are orthogonal against each other, but with real numbers. Yeah, so you have matrices here. U is in this, if and only if U transpose equals to U transpose U equals to identity. All rows are orthogonal and all columns are orthogonal. One of them is enough to prove the other. And then, so here the determinant can be plus or minus 1, right? Because the determinant of the transpose, so you get this determinant ut is equal to the determinant u times the determinant of this guy is the same, right? So I get the determinant u squared, and that's equal to 1 because it's equal to identity. Then the solution here can be plus or minus 1. Now, if we allow complex numbers here, then it's called a unitary group, and it's denoted u of n. And then here you get a complex conjugate. So you basically, on this guy, because now the identity for this is like that, where the star means taking the transpose and the complex conjugate. So then you get this, and now of course the determinant can be any complex number on the unit circle, right? So, and then in both of these cases, you have the special orthogonal groups. This is the one where the determinant is plus 1, and the special unitary group is again where the determinant is plus 1. And all of these 4 are examples of groups. And we can think of them a bit like how we parameterize complex numbers, right? So somehow these are matrices that represent some sort of directions in space, yeah, just like a unit vector pointing in some direction here does with a theta, and then every number out in space can be written like r times e to the I theta, right? So then this is the unitary matrix, and this is the distance. All right, so right, but for this analogy to make sense, I need to also then introduce this space Hn, right? Which is, well, you could do a similar analogy with all possible matrices, but here we have the Hermitian ones I said last time. That is when you do it over C, then you characterize these matrices by this relationship. And I explained how that you have real numbers on the diagonal, and so on the off diagonal one, you pair them up and you have some complex conjugate identity. Now, if you do here real numbers, then those matrices are called symmetric. So when you have complex numbers involved, you take a transpose and the conjugate, you have this identity that Hermitian symmetric or self-adjoint. It has a few names. But if you only have real numbers and you have this, then you just call it symmetric. So that's a bit of terminology. All right, so staying in this situation here, then the analogy, so if we think of this somehow as R, then the spectral decomposition gives us that every matrix A can be written as U lambda, where this is a diagonal matrix, U star, where these are now the eigenvectors, so a set of mutually orthogonal guys. So these U's are in the unitary group, and this one is diagonal, so lambda. Looks like this is defined by some sequence. So now we can think of this guy is somehow corresponding to him. It gives you the direction in space. And here you have a guy with lots of real numbers on the diagonal. You think of it as corresponding to this. Yeah, so this is some sort of matrix version of just the polar decomposition of a complex number. Yeah, an analogy that works to some extent. So, of key importance in the complex plane are measures that are radially invariant, right? So if you have some measure mu on the Borel sigma algebra of C, then you can have that mu of some set E is always the same as the same measure applied to if I rotate my set a bit, right? So this is my E. And if I rotate it, and I get something like this, and the measure stays the same. Of course, if I move it outward or inwards, the measure can change. So what type of measures are those? Well, it turns out, and it's, I won't do the details now, we'll do that, it will be a good exercise in the end. But I think you can kind of feel it, that we have this arc length measure, right? So in the polar coordinate system, if I have the interval from 0 to 2 pi and the positive real axis, then I have this mapping phi that takes r and theta into a complex number C, so e r times e to the I theta, that's a parametrization. So if you want to understand a measure mu with such invariance property, it's better to go back and describe it in the polar coordinates, right? So this mapping phi basically, I mean, like I can paint it like this. So here's the theta, it stops at 2 pi, and then r goes up to infinity. So it's this little box here, one-sided infinite box that's being sent to my complex plane. And then, so now if I have a set E here, it's going to translate back to some set E here. And here we kind of see this translation invariance means that if I move this set along the theta direction, it doesn't change, right? So it's kind of natural to understand that there exists some sort of measure on the positive axis. So let's say in this situation, now I'm writing this way, there exists a measure, let's say mu on 0 to infinity, such that mu of E is equal to mu of, no, so the product measure of mu times the weight measure of the inverse image of E here, so E represented in polar coordinates. Okay? And of course, then, so then if we want to understand the measure mu, we just have to understand the measure mu, we just have to understand how it acts on the radial coordinates. And how do we get nu from mu? You take a subset A of 0 to infinity, then you just define mu of A to be equal to mu of A cross the set of all the full unit circle, so to speak, so theta between 0 and 2 pi. Yeah, so if I want to know, I have a set here on the positive real axis, and I want to know the measure mu, then I just do the mu measure of this ring here. That's what I'm explaining here. So this allows us to decompose our measure mu and such measures mu that are radially invariant here all the time. Okay, and now we want to do something similar, but for these guys, right? So in random matrix theory, for example, you have this Hermitian matrices, they pop out in some experiment or whatever, you want to know somehow the frequency of this or that type of matrix, you know? And then you need a probability measure, you need some sort of measure that lives on Hermitian matrices. And then it is common that, okay, so you have a Hermitian a measure living on these guys, probability measure, let's say, and then it is very common then to have this sort of translation invariance. And if I take a set E here of Hermitian matrices and a fixed guy U, then here, you know, Haar measure should be invariant between left or right multiplication, but that will make me leave the set of Hermitian matrices. So I have to do this. This is an operation that allows me to stay in. So this is just like we saw here. Like I take this E and I shift it around intuitively. Okay. So if you have this sort of rotation invariance of the measure, then how can we characterize it? So somehow intuitively, you would say that when I have this, it's only the eigenvalues that matter. So I should somehow be able to write this measure mu as a measure that acts on the eigenvalues times something which looks the same all around all the unitary matrices, right? That doesn't change depending on which side of them you are. And that's what Haar measures are good for. So it tells you, because now, I mean, it tells you that such a measure exists. How to construct it is a different thing, but once you know existence, at least that becomes, you don't need to worry about that. So because this now, the set of all unitary matrices, this is a complicated object. So it's not at all like this mapping. You know, last lecture I painted a circle, and then I say, well, we can straighten it out. So we just identify it with the open interval, sort of with the half open closed interval from 0 to 2 pi by this trivial map, right? So the theta here goes into corresponding one with that angle theta. Maybe theta should be over here. So here, how do we characterize these? Well, first I need to get a vector here of length 1, which means I can choose, first I can choose 2 complex numbers for the first one, then I can choose 2 complex numbers for the second and go all the way down. When I come to the last one, I only can choose 1 complex number. Well, I can only choose the angle, right? Because well, first of all, when I'm choosing these ones, I'm restricted by the fact that the norm shouldn't be bigger than 1. And if I've satisfied that, when I come down here, I can only pick the angle of the last complex number, but not the modulus, because the norm of the total thing needs to be 1. So here you have like 2n minus 1 degrees of freedom. And then when you start picking the next one, column, you are free to pick what you want until the last two, but then you have to make sure that it's orthogonal to this one and also has length 1, so you get all sorts of restrictions, right? That doesn't mean that, so if you think of this as some sort of circle, just higher dimensional, right? And then we want to parameterize it. Now we have lots of different, we get R to some high dimensional, I don't know how many, what was actually the dimension of this object here. It has a dimension. And now we're getting into differential geometry, but you get some, you count the degrees of freedom you have, and then you get some number here that we call that M. So then from Rm, I can send, let me go this way now. I don't know if it's pi any longer, let me call it psi. So I can parameterize all unitary matrices, but I always get a problem. So as I said, this one has to, I get a problem at certain points. So when I come here, if all these first points are chosen, if they sum up to 1, then I have to choose 0 here. And that's not, then I get some sort of singularity. I cannot go left and right from 0, because then I'm out, right? So that's just like when we do from the circle, from the interval, you get a problem. I always have either, this point or the North Pole or the South Pole, somewhere you have to, where things meet. But then you can always parameterize in a different way. So if you start here, right? And this is your 0 angle, then you go around, then you come back here, and your problem is here. But you can start parameterizing here, think of this as 0, and then you count like here's, you put your angle there, then you don't have a problem at this point, but you have a problem here. So that's, okay, again, we're in differential geometry. So you can always, like, locally, you can make a bijection between your unitary group and some Rm where M is high. And that's also how we give it a topology, right? Because I mentioned, so what we're dealing with in this chapter is locally compact Hausdorff groups. So that's groups with a topology. And the topology has to be locally compact Hausdorff. So how do we give it a topology? Well, naturally, once you have a bunch of these maps phi, you just, because Rm has a topology, so you just send the open sets forward through this map psi, and you get open sets here, or a basis of open sets. Yeah, and then you have to do this, you have to check that there are different size depending on, you want to cover all the special points, and then you want to make sure that there's no inconsistencies and so on. This is differential geometry, but it can be done. So this is a locally compact Hausdorff group at the end of the day, where all of these 4 become, but they are not easy. So these parameterizations exist, but they are not good. It becomes a mess to work with this object here in this way, right? So it's just very much nicer to think of it as something, it's a high dimensional group, and it has a measure on it, and it's the Haar measure. And then you don't need to, or in many cases, you don't need to worry about parameterization issues. All right, so we want now a Haar measure on let's say the unitary group, right? So I would like to give that a name, which is a new all the time, but I think we overuse new. It would be nice to call it H. It's just that the Greeks seem to have the same problem as these Latin Europeans. They cannot pronounce H, right? So have you heard a Frenchman pronounce Hancock Tower? Hancock Tower. What? The Hancock building. The Hancock building. About to choke, right? So apparently the Greeks has the same, because they have no letter in the alphabet for, just like the Russians, by the way. I think it's only in Northern Europe where this works. normally find, you know. So anybody who's been to the McDonald's in Moscow, you want to, you know, get a hamburger, you need to order a gamburger, gamburger. Я хочу один гамбургер. So, what sort of symbol do we give this? Well, inspired by the Russians, the closest thing they could find was the G. And the Greeks have something for G as well, that's gamma. So we go with that. So gamma is now Haar measure on the unitary group of a degree of n by n matrices. And then U is a measure on Hn. I don't know, maybe for consistency, maybe this n should be down here, but well, okay, too late now. This is the way it is. Such that, and then we want this rotational invariance. U here is fixed and E is a set. Yeah, it's not a matrix, it's a set of Hermitian matrices. Now, what we can do is then that we define U of, okay, so pick a set E, which is a subset of Rn, right? And define a bit unusual, and then we define big E to be the set of all matrices of the form all Hermitian matrices with the diagonal values lambda. Lambda is in Rn. So lambda is a member of the set E, and U can be any guy from the orthogonal group, right? So that's precisely what I was doing here, right? It's just a multi-dimensional version of doing this. And then we define mu of little e to be equal to mu of big E, right? So now this is a measure on Rn, actually is a Borel measure because the topology of this space here is such that this mapping here is continuous. So now I have to find a Borel measure on Rn. Yeah, so this is something we understand. Just n diagonal, the elements, so the eigenvalues. This is something which is easy to characterize. It can be then absolutely continuous with respect to Lebesgue measure, and probably we can just evaluate n by integrating some probability density function rho against Lebesgue measure on the n-dimensional space. Not necessarily, but if this measure is nice, then absolutely continuous, then we have such a representation. And yeah, this will be a probability measure, meaning that the total integral is, you integrate over the full space, you get 1. If that was a probability measure to begin with. And then, okay, so now we have this measure mu, but how do we get back to mu? So it turns out in this circumstance, and it's not very hard to prove, that the original mu is now equal to mu times gamma, in the sense of previously that here we need to have, right, so if we define on Rn Cartesian product or with un, a map here psi to Hn. Now this is it's surjective, at least probably different unitary matrices can give rise to the same. This is not really unique. So, but anyways, this way, so there's not a bijection most likely, but we will get this nice property that mu of E is the same as if we look at the product measure of nu times gamma, and then the pre-image on the side of this set E. This is a -1 here, pre-image. And that's one example of the usefulness of Haar measure. So now this measure mu, which lives on this very high dimensional complicated thing. Well, if you're a student and you see this the first time, maybe you see that this looks like some junk here, but this is really much easier to work with. So yeah. And of course, in every locally compact Hausdorff group, you can probably by hand construct some sort of group invariant measure and see that it exists. So Haar's theorem was basically taking a bunch of such statements and realizing that, well, here's a general theme going on here. I can abstractify this and say that these measures always exist when you have a locally compact Hausdorff group, not this particular or that particular group. So that's what chapter 9 is about. Right, so this got much longer than I expected and a bit more involved as well. I just wanted to give like a brief idea of why we're going to look into the chapter 9, but I think it turned into if I keep lecturing now on actually chapter 9, you're probably pretty smoked by now. So I'll do this like a teaser to chapter 9, and then I'll do lecture on chapter 9 separately. How about that? Oh, thank you. Oh, yeah, I thought it was a good idea myself.